Welcome to A Play on Nerds.
I'm Steve.
And I'm Jarman.
Between us, we have more than 30 years of experience in the nerd arts.
Each week, we endeavor to bring the world of nerddom to all of you.
So push up your glasses and listen up, Internet.
This is A Play on Nerds. Welcome, everyone, to episode 32 of A Play on Nerds, the brand new 2015 episode. This is Jarman.
This is Steve, and welcome to the new year.
Welcome. We have a great episode for you today. Today we'll be interviewing an old friend of mine, Ian Cohen, who is a space expert. You'll hear all about it later, but he's going to school us on all the ways of space.
He is literally a rocket scientist, people.
Literally a rocket scientist.
A legitimate expert who's going to make us feel like children.
And yeah, and if you listen to our space episode a few weeks back, he's going to say all things that we had wrong. We had a lot wrong. So
yeah, we did.
Please stay tuned for that. But what were you up to these last couple of weeks, Steve? How was your new year and all that?
Good. Christmas, parents came in, had to entertain them. I got to take my mom to a distillery tour in Brooklyn, the Widow Jane bourbon and whiskey place. And that was interesting. And my dad took my wife Anna to the Pinstripe Bowl at Yankee Stadium, where Penn State was playing. And then, let's see, for New Year's, we played it pretty low-key. Didn't really do a whole lot. How about you?
Well, I'm just surprised that your mom drinks bourbon. That's pretty cool.
Oh, yeah. Oh, does she drink bourbon? Oh, yeah.
That's awesome. Well, for my New Year, let's see, I went to a couple parties, and one of the parties I actually won a pizza roll eating contest, which is kind of depressing, but yeah. Don't ever do that. It leaves your stomach feeling...
I'm sure that was rough the next day.
Yeah, it was very rough the next day, so don't recommend it.
Not even the people that make pizza rolls recommend doing that. So.
Yeah, it like blocks up your system. It's a lot of sodium and calories you don't want, so that was a thing.
A lot of fake cheese food product.
Yeah, a lot of fake cheese food product. That's how I rang in the new year. But yeah, Christmas went well and all that jazz, so it was a good time. But
did you get anything good for the holiday?
Well, actually, yeah, I got a lot of good fun Star Trek stuff for my family. Ooh. And I actually got a lovely new editing keyboard from my mother, which is fantastic.
Ooh, fancy.
Lots of coffee stuff from the girlfriend. So I like a lot of my coffee. So it was a good time. What about you?
The two sort of standout gifts, I got a ugly Christmas sweater for my brother that has gremlins all over it.
That's fantastic.
So that was perfect. And then I forgot the other one, so it must not have been.
Screw your other gifts.
I got some seasons of Fraggle Rock on DVD, a few other things, but nothing major.
Very cool. Fraggle Rock on DVD is awesome. They were all at Dragon Con last year, all the Fraggles.
What?
Yeah,
really?
A lot of the voices and and they brought the actual puppets and everything too.
Okay. Yeah, I guess Fraggle Rock, a lot of the female performers from Fraggle Rock are still alive.
Yeah, exactly. Not the dog.
Steve Whitmire's alive.
Oh, okay. He's not a Muppet dead hands?
Well, he did the ass of the dog in the tail, so I'm not sure if that counts.
I see. Just the ass.
It was one of his first things. It was a big thing for him.
It's time for Nerdy News.
All right, so jumping into the nerdy news of the new year, something happened just a few days ago, maybe like a day before the new year.
Okay.
NASA and different space organizations have been monitoring what they were calling, to get news attention, a mysterious object near Milky Way's black hole. And they are thinking it was a gas cloud, this giant gas cloud that kind of swirling around the black hole in the center of our galaxy. But apparently it's not acting the way a gas cloud should. So some theories are saying that it's actually like a, darkened star that's actually swirling around basically the toilet bowl of our galaxy. And so they're basically really excited about it because soon it might actually be sucked into the black hole. And we
might be able to witness it.
Exactly. And since black holes are so theoretical and stuff, they're actually going to be able to see something being eaten by a black hole, which is kind of cool. So I'm going to keep my tabs on that and see what's going on, because that'll be kind of, see if it goes in the future or something.
I'm just sad it wasn't an alien ship.
Oh, it was aliens. You didn't know that? Yeah.
Yes. It's all aliens. It's always aliens.
It was actually Godzilla going for a stroll around our galaxy. So there you go.
Hey, that's Lord Godzilla. Thank you very much.
Lord Godzilla.
Well, this week I bring us, as always, I love animal biology. So I thought this story was just so good. I call it Songbirds. So these scientists at the Oregon Health and Science University have been studying, what are they? Finches, studying how they teach each other to sing, and they're comparing it to human language. They've been doing all these studies on how songbirds the patterns they use might be like the basis for speech as we know it, or communication as we know it.
Oh, geez.
And so what they decided to do, and this is where I just get tickled pink by this article, is they were like, well, we should see if when we get these birds drunk, if they sing like drunk people.
Oh, God, that's horrible.
And so they came in one day, in the water, they mixed 6% alcohol and juice into the bird's water. The birds drank it and then started singing like drunks. And they sang slurred and had much less like direction to how they were singing, and they also got quieter and then louder all of a sudden and had trouble controlling how loud they were being.
Sounds familiar.
Yeah. And so it just, I guess, proves that drunk birds are like drunk humans. But the science behind this baffles me.
I wonder how PETA feels about this, getting birds drunk.
Yeah, and like here's a quote from this guy, Christopher Olson, who was the head of the study. We just showed up in the morning and mixed a little bit of juice with 6% alcohol and put it in their water bottles and put it in the cages.
That's awful.
That's a quote from it. Like, that's all we did. Science.
Scienced. There you go.
Oh, man. And so, yeah, so that's apparently what science is now. Let's get birds drunk.
Oh, my gosh. Well, I'm perfectly okay with that. I'm sure those birds had a great day, but a horrible day the next day.
That's true. Bird hangover. That's what we should be studying.
That's perfect for the new year. We all had hangovers, so there's a bird hangover.
Bird hangover study.
And so now I guess we'll jump right into our interview with Ian Cohen. All right, so now we're going to start our interview with the wonderful Ian Cohen, who is a physics PhD candidate at the University of New Hampshire. He is my also buddy from college. Back in the day, we did a lot of theater together, which is good times. I think was I your first director in theater, Ian?
You were, in college, yes.
Wow. How was that?
Started my career off in the best way possible. That's all I'll say.
Yeah, his long career of acting went from there.
Yeah, exactly. Which I quickly gave up some of physicists, much to my mother's chagrin.
Instead, he did things that are actually important and for society.
Say. So now he's a scientist, and I work at a retail store.
I'll say, though, that I think my mom is legitimately upset that I gave up acting for science.
What?
Like,
why?
First mom ever, yeah. She's like, you sure you don't want to do acting? You don't want to be an actor?
She just wanted you to shine.
Yeah, exactly.
Whatever you'd be happy with.
How I, study stars, so.
There you go. So basically, if you want to, just give us a rundown of how you got to where you are, a little bit about your education, and what's going to qualify you to basically completely school us in the realm of space.
Yeah. Sure. So I think my biggest credential is that I went to space camp when I was 10.
Awesome.
Of
so
course.
That obviously sent me down the path of greatness. And not only did I go to space camp, but out of the 600 kids at space camp when I was there, I won one of the 2 Right Stuff awards. So I've got the right stuff.
You have the right stuff. Yes.
Awesome.
So that got the fire burning. And then went to BU, got my bachelor's in astronomy and physics, and now I'm a PhD candidate at the University of New Hampshire studying physics. I helped build instruments that go on rockets that launch into the northern lights, the aurora, to study the physics that's going on there. Also worked at the Museum of Science in Boston at the Hayden Planetarium for 3 years. And I'm a NASA Solar System Ambassador, NASA Student Ambassador, and a member of the Aurorasaurus Scientist Network.
So you basically are a rocket scientist.
I don't like to throw those words around, but if we're talking technicalities, yes.
Oh, don't be a jerk. You're a rocket scientist.
So tell me honestly, do you own anything that says, yes, I'm a rocket scientist?
I don't, but I have a shirt that has a whole bunch of equations and says, yes, this is rocket science.
Okay.
That's pretty good.
And I wouldn't even know I was being insulted, so that's good.
There's a guy in my building who has the vanity plate that says rocket scientist.
Awesome.
Nice. He's being shameless with it, but...
Oh, yeah, absolutely.
And obviously it made you good with the ladies since you're recently married, I guess? You got married not too long ago?
Recently married, yes.
Welcome to the club.
Well, actually, she didn't believe me when I told her that I was a rocket scientist. Best hook line ever.
Jokes on awesome. Her.
No, because meeting you, you're really, I mean, at least from what I remember from you, because we haven't seen each other really in like, I guess, 8 years or something, but back in the day, you're just like a happy and funny and very social guy, and you're very good with people, and people don't automatically think that about rocket scientists, so you definitely break the mold, which is awesome.
Thank you. Try.
Well, I would like to start our big science-y discussion with sort of a game I came up with that I'm hoping you'll be willing to play with me, Ian.
Sure.
All right, good. That was very tentative, but excellent. Called Explain It Like I'm 4. Because Jarman and I really tout about our ignoramitude, which I just made up maybe. And it has no bounds. So I want you to explain some concepts to me and Jarman like we're 4.
Okay.
So what's the first one, Steve?
How does a telescope work?
Well, which kind of telescopes? There are 2.
The big
There's
ones.
2 kinds?
Yeah, schooled, right? So there are 2 kinds of telescopes. There's a refracting telescope, which uses only mirrors.
Okay.
And there's a reflecting telescope, which uses... refracting telescope uses lenses. Reflecting telescope uses mirrors. So with any type of telescope, the idea is you're trying to collect as much light as you can. So however big a telescope is, when somebody says that they have like a 4-inch or an 8-inch or 3-meter telescope, whenever they say a size of a telescope, they're always talking about the diameter of whatever their light collecting surface is, whether that's a lens or a mirror.
Oh, okay.
So the way that a telescope works is that either the lens or the mirror collects light from whatever object you're focusing it on and focuses that light to a point. And from that point, you can look or put it on a CCD, what we use for imaging, like a camera, and see the object. And by pairing that large mirror, right, the one that has some size that allows you to collect light, with a smaller mirror that we call the secondary. So the big one's called the primary. The second one's called the secondary. We're very creative with our naming.
Okay.
That allows you to magnify the object. So it works kind of almost exactly the same way that a microscope does. But instead of looking at really tiny things and trying to make it bigger, you're looking at really far away big things and trying to make them bigger.
All right.
Awesome. That's more than I ever knew about.
Yes, I now know more about telescopes than I've ever known in my life.
Now the important thing is the way that you orient those mirrors or lenses with respect to the object that you're looking at changes what type of telescope it is. So there's a whole range of different designs for telescopes. There's Newtonian telescopes, which was first invented by Isaac Newton, obviously. There's Schmidt-Cassegrain telescopes. There's the kind that look kind of like spyglasses, like a pirate might have. Those are technically telescopes.
I like pirates. Go on.
Yeah, I mean, who doesn't love a good pirate? But the way that you orient and configure those lenses and mirrors with relation to each other will dictate what kind of telescope it is.
So there's the mirrors and the lenses, and then within those groups, there's more groups and more types.
Yeah, right. How you orient things, how it's configured. There's different types of telescopes. And then if you want to get really crazy, there's actually things called compound telescopes, which use both lenses and mirrors.
Whoa.
And that's just crazy.
Oh, man, pump
man.
the brakes. I just found out about 2. I can't take a third right now.
It's really like 2.5.
There you go. Yeah, it's a mixture of the two.
All right, next question, and we're 4.
Okay.
How big is the universe?
Well, so the universe, we don't know is the answer.
That's a shitty answer, science.
Wait, but there's a caveat. So we don't know how big it is. But no matter how big it is, we can only see a certain distance in any single direction. Because we know that the universe has a finite lifetime, right? It's only been around for roughly 14 billion years.
Okay.
So we can only look back 14 billion years because we know light travels at a given speed, right? The speed of light, 3 times 10 to the 8th meters per second.
Yep, math.
Light can't go any faster than that. So if time has only existed for that long, then the light from that very beginning of the universe could only have traveled about 14 billion light years.
All right.
So no matter which direction we look, we can't see further than that because even if the light's there, if there's objects there, the light hasn't had time to get to us.
So you can't really quite guess it because you can't see the light that hasn't got here yet, basically.
Right. So this is what we call the observable universe. So if you think about the universe as this huge thing that we have no idea how big it is, we're somewhere in there, and all we can see around is a 14 billion year sphere. Everything outside of that is unknown to us. So we have the observable universe, which is what we can actually see, and then outside that could be who knows what.
So it could be massively older than we think.
It could be.
Interesting.
But we can... Oh, okay. Sure.
Older and bigger.
All right. Well, that was... I'm still confused, but that might have happened.
I like it.
That would have happened anyway. What are black holes all about?
If you could tell me what black holes are all about, then you probably win the Nobel Prize. So I wish I knew. But I can tell you what we know. So we've never seen a black hole, really, because that's what makes them black holes, right? So basically the gravity, you have this point source. So think about the smallest possible thing that you can think of, smaller than an atom. And this is basically an infinitesimally small area of space that has mass more than our star, tens or hundreds of times larger than our star, densely compacted down into an infinitesimally small spot, into a small space. And that creates an incredibly strong gravitational pull. And that gravity gets to be so strong that even light can't escape from it, right? So light tries to get away, tries to beam out, but it can't because of the gravitational pull of that mass. So you get this radius, what we call the event horizon, beyond which we can't get any information or light out. And that's what kind of defines the black hole. So it's this area, this spherical area of space where the gravity inside is so great that you can't get anything out. You know, no matter what Matthew McConaughey tries to tell you, nothing gets out of that black hole. Now, we can't see the black hole, obviously, because none of that light is getting out to us. That's the reason we call it a black hole. But we can see, as mass gets close to the black hole, it heats up. And it falls into what we call an accretion disk. So this is kind of hot matter that's slowly circling around the black hole. Think about it kind of like water going down a drain, how it circles around before it goes down.
Okay.
Same thing. So as this matter circles around, it heats up. And that heated up matter glows. And we're actually able to see that glowing matter from the accretion disk, which gives us an idea of where black holes are, even though we can't see the black hole itself.
You can see the disturbance that it's causing, basically.
Yeah, and that's another thing. We can also see, I think you talked about this in the other episode, gravitational lensing. So even though we don't see the black holes, we can see the interaction that they're having with light that's coming from objects that are further away from them. So basically, as the light comes to us from the object that's far away, if it interacts with something that's massive, like a black hole, the gravity can actually distort the light and gives us kind of like a blur. It kind of stretches it out into a blur on the image, and that can only be caused by interactions with something that's really massive.
That's right. We did talk about that. And actually, that brings me to my question off of that subject. And isn't gravity kind of a mystery as well? Like, we don't know where gravity really comes from or something like that?
So it's not that we don't understand gravity. We understand gravity really well. And actually, understood gravity for a long time. Since Newton kind of came up with the idea of his idea of gravity, we've had a pretty good handle on it. And then Einstein came around, in the early 1900s and came up with the idea of relativity, and that affects gravity. So I'd say since Einstein, we have a pretty good handle on gravity. What we don't necessarily understand is how gravity fits in with all the other forces that we know of in the universe. So there's 4 forces that we know of, right? So there's gravity, there's electromagnetism, there's the strong nuclear force, and the weak nuclear force. So those are the 4 forces. And gravity of those 4 is kind of an oddball because it's by far the weakest. And we've actually, in what we call the grand unified theory, or the theory of everything, as they call it, we've been able to figure out how the other 3, so electromagnetism, the strong nuclear force, and the weak nuclear force, how those 3, on the really deepest, most fundamental levels, how those 3 are related to each other, how they work together. But we haven't been able to figure out how gravity fits in. So that's where this search for, you might have heard the graviton, or gravity waves. So we're trying to figure out how gravity fits into our grander scheme of everything. So right now, if we got a really good theory that explains how the other 3 work, and if we can get gravity to work in that construct, then we've pretty much figured out the universe.
And isn't that kind of where that whole the dark matter thing comes in? They're saying there's some other mass that is causing more gravity. Am I on the right track with that?
Maybe dark matter and dark energy is a whole separate thing that have their own, the whole can of worms.
Should we open that can of worms and let them spill out into the table?
We can try. Before we open that can of worms, I'll actually do something that you guys talked about in the last episode.
Oh, sure.
And you played a clip of Neil deGrasse Tyson talking about how there's only, we only know about 15% of matter in the universe.
Dark matter. I get asked what it is, and my best answer is, we haven't a clue. We don't know what it is. We look out in the universe, and 85% of all the gravity that's out there has some mysterious unknown source. We add up all the stars, the galaxies, the planets, the comets, the black holes, the dark clouds, everything out there that we can see, touch, smell, or taste. And it doesn't add up to give us the gravity that we see operating in this universe.
Not to disagree with Dr. deGrasse Tyson, but I don't know where he's getting his numbers from. So, yeah, I know, big deal, right? So I'll kind of clarify what I think he might have been talking about, but I'm not really sure what he's talking about. So basically, all of the stuff that we can see in our galaxy, in our universe, is made up of what we call baryons. So these are massive particles, things like the proton and the neutron. Okay, so these are massive particles that behave like what we would call normal matter, right? They interact with gravity, they interact with electromagnetism sometimes, they can interact with light. It's everything that we know of when we think of matter, right? Mm-hmm. Stars, planets, our friends, ourselves, anything we know of. All of that stuff, if we take all of the baryonic matter that we know of, and we add it all up, that's about 4% of all of the energy in our universe.
Huh.
Everything we know, all the stars, all the galaxies, all the black holes, everything that we know about is about 4%.
It's causing about 4% of the gravity? That's how we know it's 4%?
No. So when we kind of think about, so mass and energy are interchangeable, right? Because of the E equals mc squared, the most famous equation ever, Einstein.
Yes.
I know that one. I saw it on a shirt.
Nice. So we're gonna use the words mass and energy here kind of interchangeably because they're more or less the same thing. So we're trying to take account of all of the mass or all of the energy in the universe and try to figure out what form it's in. All of the matter that we know of, that we can see, is about 4%. And there's another 26% that's this, what we call dark matter. And the reason that we know, so dark matter has mass, right? It has the effects of gravity. It can bend light and do all of those things. But we can't see it. So that's why it has the name dark matter. So then you might say, well, if we don't see it, how do we know it's there? And the way we can figure this out is we can actually look at the way gravity acts in our galaxy and in other galaxies. And if you were going to have a galaxy, let's say you were to look at all the stars in our galaxy and you kind of take an educated guess on how many stars there are, what their mass would be, you should be able to look at the rotational velocity of the galaxy and kind of predict how it should operate. It should operate kind of like our solar system, right? So that the planets that are farther away from the sun orbit in a longer period. That's kind of what we would actually expect it to be solid body rotation. So everything would rotate at the same, kind of like a record on a record player, right? So everything is moving at the same angular rotation, the same angular speed. But if you looked at the velocity of each individual part as you go farther out, they're actually moving faster, right? Because if you're further away, you're actually moving faster than objects that are closer in to be able to stay at the same angular speed. Does that make sense?
A little bit.
Like when I used to put playing cards in my bicycle wheel.
Something like that.
Yeah.
Something like that.
Legit.
But also you're saying that it should be predictable in that
Right.
regard.
It should be predictable, but when we try to actually do that, it doesn't work that way. There's something that's adding extra mass that's causing what we call differential rotation. So basically, it's not rotating at that constant angular speed. And that is what we think is dark matter.
So would that mean that 96% of the matter is dark matter?
No. So
there's a whole 70% we don't know about?
No, 26% is this dark matter.
Oh,
so
okay.
these are 70%, right?
Yeah, 70.
70% of the universe is this other thing that we call dark energy. And we have no idea what dark energy is. It's hypothesized that this dark energy is what's causing our universe to expand, right? Because we really don't know what's causing our universe to expand. You would think that if kind of the Big Bang works in a logical sense, right? You have this Big Bang and some intrinsic initial force blew everything out. And at some point, once it stopped expanding, gravity stopped, whatever force is driving it out stopped, it would counteract and it would collapse. And this is actually one of the things that Einstein was really afraid of. When he first started thinking about this, he was really concerned that at some point there would be what we call the big crunch, right? So eventually the universe would stop expanding, it would halt its expansion, and then it would contract back on itself. So decades initially after Einstein came up with relativity, the early half of the 20th century, scientists were really trying to figure out how this would work, how the universe would ultimately end. And we actually realized that it's not expanding uniformly like we thought it would. It's not just kind of linearly expanding. It's actually accelerating in its expansion.
Which makes no sense.
Right, exactly. It makes no sense. So if you see something in kind of a physics type way, and you see something that's accelerating in its expansion, there must be some kind of driver for it, right? There's something that's causing that accelerated expansion. And we have no idea what it is. But we've given it this term dark energy. It's some kind of energy that we can't see and don't understand that's causing this accelerated expansion. And what that means for the universe is still unknown. Some people think that eventually it'll just keep expanding until there's no longer any interaction between galaxies, and you'll kind of have this heat death of the universe as things kind of putter out. Some people think that eventually, whatever energy source there is might extinguish, and then we'll have this big crunch. We really have no idea. But it's a huge field of cosmology that they're trying to figure out.
Well, it's obviously the big spaghetti monster in the sky is causing it.
Is any of this going to happen while I'm alive?
No.
Cool. We're legit then. Go ahead. Destroy whatever you want.
Yeah, there are much shorter timescales that are still longer than your life that we need to worry about. So our kind of shortest timescale of natural disasters that are inevitable and we really need to consider about ourselves with is about 5 billion years. In about 5 billion years, the sun will exhaust itself of hydrogen, and at that point, it will contract down, and when it contracts, it'll get hot enough to burn the next element, helium, in fusion. And at that point, it will actually expand back out all the way past Mars. So all of the inner planets will be engulfed by the sun in about 5 billion years.
Mankind has like 1,000 or 2,000 years left. I think we're good.
Use them wisely.
Yeah, use those 2,000 years wisely, because we'll probably get hit by a meteor before then. It'll just wipe us out again.
I'm glad you used the word meteor, because I have another thing from your last episode.
Did we interchange comet and meteor too much or something?
No, yeah. Let's play a little game called "What's That Object in the Sky?"
It's a football.
I actually, in a previous episode, I think, when we did the Armageddon and Deep Impact episode, I played a clip of Neil deGrasse Tyson explaining the difference between meteor, meteorite, and comet, and all that stuff. But I've already forgotten it. Apparently,
We learned nothing from Mr.
I learned
Tyson.
nothing.
Learn nothing. Fail. Neil deGrasse Tyson would be so upset with you.
So please recap that for us.
So you guys were talking about the idea that a comet has possibly seeded life on Earth. So I think you'll enjoy the name of that theory is called panspermia.
Yes.
Yeah. So the idea is that a comet came and crashed into Earth, or maybe a bit of an asteroid, and basically created life or seeded life on Earth. So backing up. So there's two primary kinds, most commonly known kinds of non-planetary bodies in the solar system. So there's comets and there's asteroids. So asteroids are usually made out of dense, heavy metals. Things like nickel, iron, stuff like that. And they're generally found in the asteroid belt, right? So this is the region between Mars and Jupiter, where you've got hundreds of thousands of these things, and they're all orbiting around. There are some asteroids actually that are trapped in orbit around Earth and Jupiter. So not necessarily in our orbit around the planet like the moon is, but they're actually trapped in front and behind the planet as we orbit around the sun. So these are called Trojan asteroids. And they're basically stuck in kind of equidistant or equigravitational potential points. So basically, at the distance that they are, the pull on Earth from Earth and the pull from the sun are almost exactly the same. So they kind of just hang out there.
They don't go anywhere. That's good.
Yeah, they don't go anywhere. So they're called Trojan asteroids. So asteroids are, like I said, they're kind of planetesimals, I guess would be the word. So they're bits of stuff that started to form planets in the early formation of the solar system, but then didn't create enough mass to be able to really stick together, or maybe got destroyed when something else hit them. So they're kind of bits of rocky iron metal bits that are floating around the solar system.
Are they kind of like planetary fetuses that are just dead and floating around?
Kind of. They're not necessarily that big. There's only one asteroid that we know of that is large enough to be spherical. And that's Ceres, which is the largest asteroid. That's in the asteroid belt, but it's roughly the diameter of New England.
Interesting.
Give you an idea of size.
Well, New England's not that big.
It's not that big. Asteroids are rocky and metallic. That's the big point, metallic.
Gotcha.
So comets, on the other hand, comets are rocky, so they have something in common, but they're also icy because they live much further out in the solar system than the asteroids do. So these comets have really long elliptical orbits that take them really far out in the solar system, almost to the very edge of the solar system, and then they come back in and orbit close to the sun as they make what we call their perihelion, so their closest point to the sun. So they come in, and as they come into the solar system, they get heated by the sun's intense light, and that's when you see them glow, right? Because they're made out of ice. So as that ice melts, it begins to evaporate off the body. That water vapor then reflects the sunlight and makes it nice and clear and visible in the sky. So that's why you can see comets in the sky, usually fairly easily with a telescope or even sometimes with your naked eye.
Now, if the ice melts off a comet, does that mean it becomes an asteroid?
Yeah, if they're always giving off, that was my question. If it's always like floating off, wouldn't it just dry up?
And then it would become an asteroid at that point, right?
So eventually, so they don't become asteroids. They would just eventually actually break up.
Gotcha.
Because the ice melts and all the rock breaks apart, and they actually break up. So a lot of the meteor showers that we go through every month, so there's pretty much meteor showers every month of the year, and they repeat every year. So things like the Leonids or the Perseids or the Orionids, those are usually caused by the dust and the dust trail left by a comet. So if you think about it, as the comet zooms through the solar system, it's leaving behind this debris trail, right? Because as that water and ice evaporates off, the rock that's being held by that ice is crumbling away and going out into space. So it leaves kind of this dust trail behind it. And that dust kind of just settles there and falls into a kind of easy orbit around the sun. And as Earth orbits around the sun, we keep encountering that dust trail that the comet left. And as we ram into that dust trail, we get the next thing that we want to talk about, meteors. So meteors, okay, are the things that you see in the sky coming into the sky, right? So any object can be a meteor if it enters Earth's atmosphere and burns up.
So if I threw a sandwich and it went through Earth's atmosphere and burned up, that'd be a meteor?
That would be a meteor.
Sweet.
If somebody on Earth sees it in the sky burning up, it is a meteor. So I will one-up your sandwich. Astronauts that are out in space, let's say they're spending 6 months on the International Space Station. Everybody poops, right?
Yeah.
So they actually collect all of their waste and then jettison it back into the atmosphere where it burns up.
It's a poop meteor.
When you're wishing on that star, it could be an asteroid that...
So wait, that's got to be on like a schedule, right? There's like one country that gets to watch a meteor shower of poo all the time.
It might. I'm not. That's above my pay grade. I don't know.
I hope it's Sweden.
Not my service level.
Well, basically, the comet is pooping on us meteors anyway. That's what it's doing as it passes by.
More or less. You can think about it that way.
Well,
We're bringing it down
I will
to our
think
level.
of it that way because I'm pissed at that.
So meteors are the actual burning thing in the sky. The object that's coming in to create the meteor is called a meteoroid.
Okay.
So we've got a little technical jargon there. So the object that's coming in is the meteoroid. The meteor is the actual visible thing in the sky that's burning up.
So they really are one and the same thing, though.
They are, but you can kind of think about the meteoroid as being a step before it becomes a meteor, right? So the meteoroid is coming in and then becoming a meteor as it encounters the Earth's atmosphere. But a meteoroid can be a comet, it could be Steve's sandwich, it can be a piece of ash, it can be anything. But so the object that comes in is the meteoroid.
Gotcha.
And then it burns up and you see a meteor. And then if that meteor is the right size and it's large enough to actually make its way through the atmosphere and it lands on the ground, then it is a meteorite. So that the piece, anything that makes it to the ground from space is a meteorite.
Why do they all have different names? Why wouldn't it be?
Yeah, this is the dumbest naming convention ever. This is worse than French.
Because it helps clarify the different stages, right? Because not all meteors make it to the ground and create meteorites. Gotcha. So you can have an object that's not large enough to actually make it through the atmosphere. Because think about it, as you're coming through the atmosphere, you're heating up, you're burning up. Sometimes you can even get what we call boli. So this is basically something coming through, and the pressure and the heat from the reentry can cause it to explode. So what they experienced actually in Russia a couple of years ago, remember when there were all those dashboard cameras when they saw this huge thing come in and there was a pressure wave that blew out windows and stuff?
Oh, yeah.
There was no actual meteorite from that because it ended up being destroyed by the pressure and heat that was created. And that cataclysmic explosion causes a pressure wave that can blow out windows. So it's similar to the event that happened in northern Russia in the early 1900s where it leveled hundreds of miles of trees around.
Tunguska, right?
Yeah, Tunguska, yep. So that happened. That was a huge explosion that happened in the upper atmosphere because an object came in and heated up and then exploded. And the pressure wave and the heat that was radiated from that actually leveled hundreds of miles of trees.
Well, that's the theory. It could be aliens, so...
It was Lord Godzilla.
So roughly, an object needs to be roughly the size of a Volkswagen Beetle to be able to make it down through the atmosphere to the ground. And when it did, if something that size came through the atmosphere, by the time it actually made it down to Earth, it'd be about the size of your fist.
Gotcha.
So our atmosphere does a really good job of protecting us.
It'd have to be like the size of Texas to like actually make it through and do a lot of damage.
Just like Armageddon.
Yeah. So to give you guys an idea, there's a famous crater out in Arizona. It's called the Meteor Crater. You might have heard of it. You can Google meteor crater. It's actually really well preserved because it's in the middle of the desert where there's no rain or anything that will erode it. But it's about a mile wide. And they think that was made by something that was the size of 3 football fields.
Oh, geez.
So it doesn't need to be the size of Texas. Size of Texas is really bad.
Yeah.
But a couple football fields is something that would be significantly damaging.
And that's why I hate football.
I have a lot of reasons for hating football.
So besides our horrible misnomers, what other beef did you have with our science space episode?
Let's see. I enjoyed Jarman trying to say interferometry.
As did I.
Don't think I ever got that one.
So I can so interferometry, just for a little background, is basically using 2 different light sources and a mirror, or what you call an etalon. So it's a surface that has 2 different reflecting sides, and by using those 2 different light beams and that reflecting surface, whether it's a mirror or etalon, whatever you use, you can actually determine how far away things are by how many times the light reflects back and forth through the object. So it's something that's used in astronomy. It's used actually in lots of modern technology today. They use it for lasers. They use it for all different types of particle physics and things like that. So interferometry is pretty common nowadays, but we do use it for astronomy.
Oh, yeah. I got one at home.
Yeah, exactly. Yeah, they make little pocket ones now. It's useful for everything.
I printed one out of my 3D printer the other day.
I love my Mr. Interferometer.
At least we know how to say it.
Interferometer. The other thing that I wanted to point out was that you guys were talking about a megaparsec. I think Jarman said that it was something to do with the distance between the Earth and the Sun,
or something like that.
Yeah, I remember thinking, "Oh, that sounds right."
It's not even close.
Damn it!
So we do have a name for the distance between the Earth and the Sun. That's called an astronomical unit.
Oh, I've heard that. Okay.
It's about 93 million miles.
It's an
between the Earth and the Sun.
Astronomical unit.
So that's kind of our smallest it's our smallest astronomical unit, right? That's kind of our base measurement in the solar system is AU, how far things away in relation to the Earth-Sun distance. So once you get out of the solar system, AU kind of aren't helpful anymore because then you have tons and tons of AU that need to be counted up, and then you might as well just use miles because they're ridiculously tiny. So the next kind of scale of cosmic distance is the light year, right? So this is literally how far light goes in a year.
Yeah.
So that is roughly 64,000 astronomical units, or roughly 6 teramiles. So 6 times 10 to the 12th miles. That's a light year. So then we get to a point where light years actually aren't even helpful anymore, right? So our closest star to Earth is the Sun, right? So that's our closest star. And that's about 8 light seconds away. So if we think about a light year, it's 8 light seconds. It takes 8 seconds approximately for the light from the surface of the Sun to get to Earth. So the next closest star to Earth is 4.2 light years away. So to kind of give you a scale of how ridiculously big space is, scaled like that. So if the Sun were the size of basketball, okay, so let's picture a basketball, right, about 12 inches in diameter maybe. If that were the case, and it were sitting on home plate in Fenway Park, I'm going to use this analogy because it's the one that I used to use at the museum. So if the Sun were the size of a basketball sitting on home plate in Fenway Park in Boston, the entire solar system would fit inside the infield.
Okay.
The next closest star to us, Proxima Centauri, would be sitting on top of the Great Pyramid of Giza in Egypt.
Wow.
Holy Toledo.
So the entire space, think about the entire space between Fenway Park, infield, and Egypt is empty.
There's just nothing there. That's why I've always wondered about that too, about that empty space between solar system?
Well, there's a lot of dust actually, and then there's also particles that have come streaming off stars. There's what we call the stellar or solar wind. There's a constant stream of particles coming off the sun and other stars. But dust is actually the more important thing. So this leads to something that's actually one of the oldest astronomical question since the dawn of man. You can kind of think about this as the oldest astronomical question. So if we think about this, knowing nothing about space, nothing about the sky, we figure out that there's billions and billions of stars, right? We can look up at night and we see all of these stars like our sun. So the question is, if there's all of these stars out there, billions of them in our galaxy alone, if there's all of these stars, how come we have night?
How come we? Because the light's not bright enough from those other stars, right?
They're that far away.
No, it's not that. That's kind of our intrinsic answer, right? The idea is these things are so far away that there's no way we can see the light. But that's not actually the case. It's if we added up the light that comes out of our sun's just kind of a normal middle of the range star.
Yeah, it's okay.
If we add, yeah, it's just everyday old sun. But if we add up the light from all of those different stars, it should flood the sky. And the question is, why doesn't it? And that's because there's dust in our galaxy. And the dust can actually, even though they're itty bitty tiny grains of dust, there's enough of them scattered throughout the immense space of our galaxy that it actually diffracts the light away from us.
That's pretty fascinating.
And causes it to be dark.
So we're pretty thankful for that dust then.
Yeah.
I was just hoping it was dark magic.
Dark magic.
Dark magic. That idea, that concept is known as Olber's paradox.
But where'd the parsecs come in? I think we were originally talking about parsecs.
Yes, the parsec is the next step out from light year. So one parsec is 3.26 light years.
Where'd they get that number from?
Where the hell did they get that? 4? No, not 4. 3.26. Put it down.
So it actually comes from something called parallax. So it's one of the ways that we can measure how far away the objects are from the sun and from Earth. And by using that measurement technique, so basically what you do is you look at an object at one part of the year, and then when the Earth's on the other side of its orbit 6 months later, you take another measurement. And by looking at the angular change between the object that you're looking at and other stars, you can get a distance. And if you use some simple trigonometry, it's actually much easier to use a parsec as 3.26 light years. So that's kind of how it was defined. It's because that system makes the math a lot easier if you can define a parsec as 3.26 light years.
It's funny how you use the oxymoron simple trigonometry.
Yeah.
Oh, yeah. What's the sine or cosine between friends?
That's like triangles and stuff, right?
Right, exactly.
Got it. I know that
triangles.
one.
So of course, this leads back to the nerdiest thing that I know of, and it's the fact that George Lucas made a huge error in Star Wars: A New Hope and tried to make it sound like Han Solo knew what he was doing. He says this is why normal people shouldn't be able to use science jargon in movies, because they always get it wrong.
Oh, apparently they've like tried to explain that away and saying that the guy explaining that actually meant distance, and like the race is like
in the book he tries to kind of wiggle around that, but that doesn't make any sense because the question that they asked to Han is it fast? Speaking about the Millennium Falcon. So it doesn't matter. You could run the Kessel Run in a shorter distance, but that wouldn't have had anything to do with how fast the ship was.
Yeah, they tried.
Yeah, you know what? I give them the credit, but they should have just fallen on their sword at that point.
I think we're all trusting Han too much here that this ship actually did that.
Right.
I think that's really where we need to draw the line.
I think Han had heard the term parsec somewhere and just decided to use that.
He just picked it up from
Didn't he just come from killing a guy? I mean, come on.
Yeah.
Yeah, let's get in the ship, guys. We're going across the universe.
And see, like, a Jedi doesn't know what a parsec is. He just knows about magic stuff. So he's like, whatever.
Right,
Dark magic.
Dark magic.
And this devolved quickly.
So did you have one more question on there, Steve?
Yeah. So final question. What kind of a dinosaur is an Aurorasaurus?
The best kind of dinosaur.
What is that?
So, what is an Aurorasaurus?
Yes.
So Aurorasaurus is a NSF-funded project that is trying to get citizen science engaged in aurora. So citizen science is basically the idea of scientists getting everyday people, right? You, me, your friends, to help participate in science, because there are some jobs that are just too big for the scientists to do. So we try to farm it out basically and get the community involved. So there's all kinds of citizen science type programs around. You might have heard of like Galaxy Zoo and that whole range of things that they have. They have one associated with the sun too. There's small, simple tasks that any person can help with, like classifying galaxies. So you can go on Galaxy Zoo and help us classify thousands and thousands of images of galaxies, what kind of galaxy it is. Because honestly, it would take a lot of time for scientists who have more training than you need to do that. So we can easily teach somebody, any kind of general citizen, how to do that, and they can help us out. So Aurorasaurus is something that's specifically trying to get citizen science involved with the aurora. So the aurora are the northern or southern lights, right? These are light displays that are caused by particles interacting with our atmosphere. Well, so we can go back to the aurora. So this is my bread and butter. If you really want to talk about the aurora, we can do that in a second. But Aurorasaurus basically takes Twitter, right, and searches for where and when people say that they see the aurora. And using that data, we're actually trying to make a more accurate predictive model of where the aurora can and does occur. So you can go onto aurorasaurus.org or download the Aurorasaurus app and either tweet and participate, say, I see the aurora or don't see the aurora, or you can help verify tweets by going through and looking at the tweets that have been cataloged and say, maybe somebody's actually talking about Aurora, Colorado and not the aurora. So you can say, no, this person isn't seeing the aurora, and you can help out in verifying and enhancing our algorithm. And then you can also sign up to get alerts. So let's say you live in Minneapolis, for instance, and you want to know when you might see the aurora. You can actually sign up to get an alert from Aurorasaurus that will tell you when there's increased geomagnetic activity and when you might be able to see the aurora.
Bam.
So there's a bunch of different layers. You can help verify the tweets and improve our algorithm. You can tell us if you do or do not see aurora, and then you can also sign up to find out when you might be able to see the aurora wherever you are. So the Aurorasaurus is the kind of dinosaur.
So is that like thesaurus, and that's why they did that, like the Aurora thesaurus or something?
No, I think it just sounded cool. It was picked by so.
That's a first for science. It sounded cool.
Yeah. Better than all those ridiculous acronyms that we come up with.
Well, I'm glad that we kind of naturally plugged that.
Yeah, that was a very smooth plug.
Yeah, we didn't even plan that. That was excellent.
Thank you.
Also, we were going to ask, what exactly, because you have a whole blog about this, about the societal impact of the field of heliophysics. So explain to us, talk about your blog and what exactly is heliophysics.
So heliophysics, kind of in the general original term, is if you just break it down Latin, right? It's the physics of the sun, helio. So it's the study of the sun.
I was right, Steve.
So the study of the sun. About 20 years ago, it was brought in to really mean the study of not just the sun itself, but also the sun's interaction with the rest of the solar system. So not just how the sun works and the sun itself as a star, but also how its magnetic fields, how its solar wind, the particles that are constantly streaming off of the sun, how all of that interacts with not just Earth, but every planet in the solar system. So it's easy for us to kind of, think about the sun as being this big ball of fire that's 93 million miles away. And yeah, it comes up every day because the Earth rotates and it gives us warmth, and that's great. But there's a lot more going on in the system that we don't see that can still have a big effect on us. So to kind of give us some scope, 98% of all of the mass in our solar system is in the sun.
Jeez.
So, yeah, everything else in the solar system, all the other planets, all the comets, all the asteroids, all the dwarf planets, all of that stuff is 2% of the mass.
Well, I didn't feel insignificant before, but now I feel insignificant.
Well, I'm glad I can help.
Man.
So 98% of the mass is in the sun. So it's when we think about the solar system, it's mostly the study of the sun and then how that affects everything else, all the little bits. So you have this massive object that's obviously dominating the gravity, right? Everything else in the solar system is orbiting around it. But it's also got this really strong magnetic field that's coming out and basically pervading the solar system. And that's good because it helps us, it actually keeps us protected from some other external things that happen in the galaxy. There's things like galactic cosmic rays. These are extremely, extremely high energy particles that are caused, we think, by supernova in the galaxy. These particles are basically flying all over the galaxy. And actually, in times of increased solar activity, when our sun's magnetic field and our solar activity gets more intense, it actually does a better job of blocking out those galactic cosmic rays. So that's good. So the sun is kind of it's carved out a nice little safe place for us in the galaxy by having this magnetic field and solar wind that kind of helps protect the boundary of what we call the heliosphere, right? The region of the magnetic field of the sun.
So I'm guessing those galactic rays would not be good for us. They wouldn't give us superpowers. They'd probably just kill us.
No, they're not like gamma rays.
Gotcha.
Noted.
So no hulking. Actually, there's some scientific papers and medical papers that actually think that galactic cosmic rays might be the cause of some birth defects.
Oh, geez.
Yeah, think about it. They're basically flying all over the place all the time. They're really high energy. If they hit a forming cell, they can do damage. So
makes sense.
Weird.
Wow, good. That's something else to be afraid of.
Right. So there's this whole, right, the sun's carved out this little area for us to live in, and that's all well and good and everything's happy, except that there's this other activity that goes on in the sun, right? The magnetic field of the sun is constantly changing and moving around, and that can cause all kinds of activity, things like solar flares, solar prominences, what we call coronal mass ejections. So that's literally just tons of hot radiated particles being spewed out across the solar system. So you kind of think about the sun like a drunk that's just kind of vomiting every once in a while in every direction. And if those hot plasma blobs of radiation get vomited in our direction, then it hits Earth's magnetic field. And Earth's magnetic field does the same thing that the sun does. It does a really good job of protecting us from the sun, right? You can kind of think about the Earth as like protecting us from that crazy drunk.
Really fat, heavy drunk, obviously.
Right, really fat, heavy drunk. And actually, we think that the magnetic field is actually what's it's one of the main reasons why we're able to survive with life so long on Earth. We know that Mars used to have a magnetic field because we can see the traces of it in the rocks on the surface of Mars. But we know that it doesn't have a magnetic field anymore. And as that magnetic field died, what we think happened is that the solar wind, those particles that are constantly shooting off the sun, slowly ablated away the atmosphere. So basically, as those particles interact with the atmosphere, it slowly strips away the atmosphere. And over a long period of time, you eventually end up with no atmosphere. And then the temperature drops, and all the water is evaporated away, and you have a dead, cold, lifeless planet like Mars is today. So our magnetic field is what's keeping our atmosphere from being stripped away by the sun. So it's really good. But sometimes there's things like solar flares and coronal mass ejections that can severely impact our magnetic field. So if you have a coronal mass ejection, tons of hot radiated plasma that's ejected by the sun, and it hits Earth dead on, it's going to cause reverberations that are going to basically travel all the way through our magnetic field, through what we call the magnetosphere, the realm of Earth's magnetic field, and those will eventually make their way down to Earth. And when that happens, you can get what we call geomagnetic storms. And geomagnetic storms can cause a whole range of issues, from damaging satellites. So the particles that come from the sun and make their way through the Earth system can actually cause hardware malfunctions, or can actually cause high voltage arcing that can damage satellites. So imagine that the GPS satellites go out, or telecommunications satellites go out, or national defense satellites go out. That can all happen. You can actually, it can create abnormalities in the Earth's atmosphere that can cause interference with like high frequency radio communications and things like that. And one of the biggest problems is that it can actually induce currents. So if you have electricity that's being generated in space, you can actually induce currents. And whenever you induce a current, it's going to try to find the easiest path that it can travel. So if a current is induced in the ground, what do we have in the ground already that we use to conduct electricity to all of our houses?
All the wiring and everything, pipes.
All the wiring, yeah, all of the power grid, right? Yep. So we've provided this very nice conduit for electricity to flow. So if there are induced ground currents, that current's going to try to find the path of least resistance to travel, and it will naturally funnel its way through our power grid and into our transformers. And if transformers blow, that can be really bad because our system's not really set up to kind of compartmentalize and reduce damage. So an example of this is in 1989, there was something called the Hydro-Quebec outage. So a geomagnetic storm caused a transformer to blow up in Montreal and Quebec, and caused the entire power grid of North America to fail. And actually they felt the power outage in San Francisco.
Jeez.
Yeah. So that's really bad.
More things to be afraid of. Yay.
Yeah. Well, you'll be happy to know that we are currently working on how to improve the power grid and upgrade it and modernize it so that we don't have that kind of cascading system failure. So we can actually, one, get some kind of warning when these things. So to give you an idea, when something like a coronal mass ejection or a solar flare or something like that happens on the sun, it takes some time for the particles themselves to get to Earth, right? They have to travel 93 million miles. So we do have some lead time. It's usually on the order of about 8 hours. Once the solar flare goes off or the coronal mass ejection happens, we see it almost instantaneously because the light travels much faster than the particles do. But it takes those particles some time to get to it. But even if the flare goes off, we don't necessarily know what direction it's going in. So we need to wait to be able to actually get our kind of upstream warning system, and that's a satellite that's called ACE, and it's actually about 20 years old. So it's really old. We're working right now. We're actually supposed to launch its replacement in a couple months, in early 2015. But once ACE, that's sitting out at what we call the Lagrange point. It's basically the equipotential point between Earth and the Sun.
I've heard of that.
Yeah, there's 5 of them, but the one that's between us and the Sun is called the L1. So ACE is basically sitting there, and it's kind of our buoy, if you will. And that's what's going to let us know if we're in any imminent danger. If the particles hit ACE, then we can say, oh no, we're in trouble. But ACE only gives us about an hour warning.
Oh, good.
So if these rays specifically can mess with electronics and that sort of stuff, what if ACE goes out?
So then we're in trouble. But ACE is specifically designed to withstand radiation. Actually, almost anything that goes up into space now is what we call radiation hardened. So we specifically design it and try to take every single precaution that we can to stop, to mitigate the damage that might be caused by solar particles or energetic particles. So we've done our best to try to stop that from happening. But you're right. It could go out. It could go out at any time, and then we're just kind of sitting blind.
Well, good.
Yeah.
Let it come. Let's go for a ride.
One of the things that we're trying to work on as a field in heliophysics is trying to get better modeling, right? So if we can try to model and really understand how the sun works and how coronal mass ejections work and how solar flares work and how all those things are driven, then maybe we can get some kind of predictive capability, right? So this whole realm of solar-induced activity, on Earth is what we call space weather. You might have heard this term before. It's kind of a big buzzword.
Space weather.
Yeah, space weather. Woo! The space weather is kind of where Earth weather was back in the 1930s, right? You might get some meteorologist that was like, I think there might be a tornado, but I'm not really sure. And then you'd walk outside and be, holy crap, there's a tornado. That's kind of where we are right now in space weather. We don't really have great predictive capabilities. We can react when something's happening, but we have no real capability to really predict when things are happening. So that's where the realm of heliophysics is trying to go, into better understanding on the most basic levels and trying to get more predictive capabilities.
Well, it sounds really important. It sounds like you're very passionate about it as well. That seems to be where you've kind of put your focus.
Yeah, it's important day to day. I mean, stars are pretty and cool, but they're not going to mess up Earth like the sun is.
And also, I was thinking while you were talking about that, how the Death Star doesn't need a giant laser to blow up the planet. It just needs something that would take out the planet's magnetic field, and then they'd be fucked.
Exactly.
Yeah, that'd be awesome. And horrible.
We should build one of those.
So I think, Steve, are we ready to move on to our game here?
Yeah, let's move on to the final game. I'm excited to hear this.
Oh, another game? Oh, jeez.
Another game. This is actually the game I think we played on that space episode, and it's Star Trek Technobabble, or real astrophysics terms.
I was afraid of this.
I didn't want to do straight up trivia because you probably get everything I asked you, so this is more obscure.
This will be good.
So here we go. Asymmetrical gravimetric disturbance.
I'm going to go with Star Trek Technobabble.
You are correct. Let's go with ionic spatial field.
Also, Star Trek Technobabble.
You're very good, sir.
Damn it, Jarman.
They try to make these are all reasonably sounding things, though, I have to say.
They are reasonable sound. That's what I tried to pick out. All right. Galactic globular cluster.
That's real.
Damn it. He's gonna get every single one right.
We're doomed.
Do I need to explain what a globular cluster is? Because I can do that.
No.
We don't want to learn things anymore.
We're done.
All right.
We're full. Off mode.
We're full. Our brains are full. All right.
Let's take a nap.
Atmospheric nanopattern.
I'm going to go with Star Trek Technobabble.
Damn it. Yes, you're correct.
Jarman.
Come on, you don't know any of this,
Pick
Steve.
a hard one.
Spectroscopic parallax.
That's real.
Yes, you're correct. All right. Chromospheric heating.
That's also real.
Correct.
Fuck.
We have a true science expert here. What do you want from me?
I know.
Or maybe am I just a really big Star Trek fan?
There you go. That could be it,
Yeah,
too.
true.
Ambient flux signal.
Star Trek Technobabble.
Correct.
Mashing together real science words in ways that don't make sense.
That's what Star Trek does
So
best.
I'm pretty sure that's on their crest.
Temporal nadion variance.
I'm going to go with Star Trek Technobabble.
That is correct.
It had the word temporal in it.
Globally hyperbolic spacetime.
That's real.
Yes, you're correct.
Well, shit.
Dimensional transmutation.
I'm going to go with Star Trek Technobabble.
That is incorrect. It's a real thing.
Yeah, eat it, nerd.
Yay, you got one wrong.
God.
Maybe I got that one wrong on purpose to make you feel better.
Oh, you did make him feel
You'll
better?
never know.
I do feel better, though.
He got 8 out of 9 correct.
And 8 in a row for that matter. Man.
8 in a row. That's the best any game we've ever done.
Yeah, that's
probably,
true.
for
That's
anyone
the best score on anything in the history of Play on Nerds.
of this podcast. Well, thank you so much for coming on. And this is just the tip of the iceberg of your knowledge, I'm sure. And if you don't mind, I think we would love to have you back sometime when like maybe another science story is pretty popular. You can come and give your 2 cents on it if you wouldn't mind.
Absolutely.
Yeah, absolutely.
Love it.
Thanks for joining us, Ian. I learned too much.
Yes. My brain hurts.
No problem. It was a pleasure. I have to say, guys, I absolutely love the name of your podcast.
Oh, thank you. It took us a while to come up with it.
It tickles me all over.
Well, that's disturbing.
Deal.
But okay, I'm glad.
Deal.
Is there anything you want to plug before you go?
Of course, there's Aurorasaurus.org.
Yeah, aurora.org. But I'll also more self-servingly plug my new blog at the center of it all, which talks about a little bit more about heliophysics and why it's important and how things work, like what is the sun?
That kind of stuff is important for people like us.
It is. We got to learn it somewhere.
It is. It's important, and it's got started, but there'll be more and more in-depth discussion as it gets going.
And I love the title of that blog as well, The Center of It All, because that's what the sun is, at the center.
Yeah, that took me a while too.
And is there any way people can get a hold of you if they'd like to? Maybe Twitter or
if
something?
they want to go to the blog, there's a contact page on there, and they can shoot me an email, ask questions, and I might even do a random Monroe type thing where if people ask me questions, I'll directly answer them in the blog.
That sounds awesome.
There you go.
But thanks for coming on, and we'll hope to talk to you again sometime soon.
Thanks again, Ian.
No problem. Take care, guys.
Well, that was a fantastic interview with Ian. I'm so glad he came on the show. Taught us so damn much.
And just blew my mind apart the whole time.
My mind couldn't hold anymore after that was over. I had to take a nap.
I understood like every third or fourth word he said.
But I did learn a lot, so that was awesome. That was definitely awesome. We'll hope to have him
That's
back
true.
again.
I now know more about telescopes than I've ever known ever.
There's so many kinds. There's two major classifications, and then
within those, there are sub-classifications.
you can mix the two together.
And lasers and mirrors and shit. It's like we're in a Bond film.
Spectre.
Anyways.
So what are we jumping into now, Steve?
I think we're going to move into some trailer reviews. Here at Play on Nerds, we have developed an interesting rating system to bring to you our ideas on the trailers we're about to review. At the low end of the scale, we have Burn It, where we think you should find every copy you can get your hands on and throw it into a barrel fire.
Kill it with fire. And our next step is Drunk Watch, which means that, yeah, I'd watch this movie. It'd be entertaining if I was under the influence of some kind of substance of some kind. But if I was sober, probably not going to check this thing out.
Nope, not going to see it. Next, we've got We'll See, which is maybe we just don't know enough about this movie to tell what the hell it's going to be.
Could be good, could be bad, not sure. And our next category would be Get the Couch Ready, which means I'm definitely going to check this movie out at home. Wouldn't necessarily pay the big bucks to see it in theaters, but I'm definitely going to watch it at home, so get that couch ready.
After that, we have Take a Look, where we are recommending for you, our viewers and listeners, to check out this movie and check out the trailer and tell us what you think about it. We wanted to see what you guys think.
It looks pretty good, but we're not quite sure yet.
Yeah, take a look.
Yeah.
Let us know.
And for our final and best category, we have Shut Up and Take My Money.
Shut up and take my money.
This looks so awesome, we're gonna see it.
That's where we cannot wait to give Hollywood bigwigs all of the money that we have earned at work to go see a film for $47. We're so excited, we just have to go see it. We don't have a choice.
And that is our A Play on Nerds official copyrighted trademark system for rating our movie trailers.
All right, so unfortunately there were not enough space-related trailers this week to go along with the space-related interview that we just had, so we just had to go ahead and choose a few. There are some. This is a rough time of year. I just want to start with that. We're in the post-Oscar nomination season.
Yeah, you really found some doozies this week, Steve.
Which means that the movies that are going to be coming out, we're seeing previews for, are ones that people thought might have been available for Oscars, but then the studios went, nah, no, they're not. And I'll start off with one that intrigues me a lot, In the Heart of the Sea, which is supposedly a real-life account of the story that Moby Dick is based off of. And it looks terrible. Bunch of guys in a boat, huge white whale pushing it. Like, there's no mystery. We've already seen the whale. We've already seen it destroy things. So that mystery is gone from the film. So my question becomes, what else can this film actually offer us?
Yeah, I put my notes, And now the movie no one was asking for, Moby Dick, the action movie.
Accurate depiction.
Also, like this, I think the trailer was just really poorly cut. Like you said, it gives away the whale immediately throughout the whole trailer. There's no mystery. Also, like they kept cutting Chris Hemsworth as the star, playing our Captain Ahab kind of character. But like they would ask him something in the trailer, like, I want you to tell me you're scared. And then we cut back to him, and all of a sudden he was clean shaven, and he said, I'm not, or something like that, or never, whatever. It's like they didn't even bother cutting the trailer well. So, and the CGI whale was just really like obviously CGI, not even very well done. Like, oof.
Well, now and then, the only redeeming factor I could see in this is in a trailer when they give away too much. The only thing that might be nice is that if that's not the whole movie, if their boat gets sunk in the first 10 minutes. And then the rest of the movie is them actually doing something interesting, or is a study piece on isolation. Like, who knows? It could be interesting if they've showed that much, but more than likely they've blown their load and we got nothing.
That's wishful thinking, yeah.
It's possible. I've seen it happen.
Yeah, in good movies.
Yes, true. In good movies.
I did see that it has Cillian Murphy, who was briefly shown in the beginning of the trailer. He played Scarecrow in the Batman Begins movie, I think it was.
Oh, yeah, I did see him.
So he's a really good actor, but I only saw a little bit of him. I don't know why he's in that movie.
Maybe they're trying to hide him.
Yeah, maybe. Maybe he'll be a secret character. Maybe he's actually the whale. I don't know.
Yes, that's the twist. It's actually directed by M. Night Shyamalan. Cillian Murphy is the whale.
Shyamalan.
Shyamalan. Twist ending.
This is probably my first burn it.
I'm going to give it a we'll see, because they could be doing what I described, which is they've given away the plot early and it's going to be about something much bigger or something totally different, which is possible still, but not like.
You're very hopeful, yes. See that?
I'll give it a we'll see.
For me, it's like this would probably be fun to watch, but I don't ever need to see this movie, so I'm actually putting it as a burn it. That's my first one, I think, ever.
Okay. We may have done one other,
maybe,
but it was just so terrible there was no way to not do burn it.
Like that Viking. No, I think that was
Ragnarok, which is now on Netflix.
Yeah, I think I would have wanted that as a drunk watch. It was just so bad. All right. So
keep in mind, drunk watch may not have existed.
That's true. Drunk watch may not have been a thing. Yeah,
because we started with like 3 ratings and it's gone up to 7 now. So,
well, our next one is Predestination with Ethan Hawke. I really like Ethan Hawke, so I'm holding out hope here. This reminds me a lot of that movie, The Adjustment Bureau, the kind of way it's set. But it's basically he's a time traveler. He's part of the time travel, police force type thing. But it's done kind of in a film noir style, and he's jumping around back and forth in time, kind of like Looper.
Trying to catch a bomber, I think, is the overall.
Yeah, here's the weird thing. Okay, so he says throughout his narration of the trailer that he's looking for the Fizzle bomber. And he goes back and forth in time looking for this guy. And in one of the scenes, you see him in the future with his face all cut up. And he says, if you could look into the face of the killer, would you kill him? Or something like that.
Yeah, the man who did this to you or whatever.
Yeah. And then, but one of the jumps, they show him jumping through time. As he jumps, the car he's in kind of explodes. And so I'm like, I think they already gave away the ending. I think he is the Fizzle bomber. He just doesn't realize that every time he was going back and forth in time, he was causing explosions. And so he's actually looking for himself. And he's just they gave it away in the trailer.
That's the ending of the film. I was going to say the exact same thing.
Really?
It was him the whole time. Either he's doing it by mistake, or his knowledge of the future leads him to be the Fizzle bomber to cause something greater to actually happen.
Yeah, because they give it away in the trailer. He's like, if you could look in the face of your killer, and he's looking at himself in a mirror, it's like, you just gave away the ending.
Yeah, it's him. He's the villain. That's the end of the film. Now the question is, how do they get there? And is it interesting?
Yeah, that's what I'm thinking. Like, why'd you give it all away? But I mean, that's why I'd say like a we'll see, because it looks like it's well shot. I like Ethan Hawke, but
see, I'm gonna go ahead and give this one a burn it. Any movie where I know the ending before seeing the film has failed.
Well, especially the trailer failed. Jesus.
Yes. Maybe that's the real victim here is the trailer.
Yep, they need to fire somebody in that department.
Done.
Well, there we go.
And then fire everybody who worked on In the Heart of the Sea.
Yes, pretty much. Chris Hemsworth, why'd you do that?
So I'm giving this one a burn it. That's my final judgment.
There we go. What's up next?
Finally, we have the movie that I think looks the most interesting. It's coming out in March, which means that it's not really Oscar contention. So that's good that they're waiting. It's called White God, and this looks like a strange movie. It looks like a mix between Homeward Bound and like Spartacus,
or like Planet of the Apes, or Rise of the Planet of the Apes.
Rise of the Planet of the Apes and Homeward Bound. If they got together and made a film, that would be this movie.
That's a good description.
It seems to be about a little girl whose dog is taken from her when she goes to live with her father. The dog gets captured and then leads an organized dog revolution in order to get back to his master.
Mm-hmm.
And it at least looks interesting. It looks like it brings something new to the table, at least.
Yeah, that's true. It's different.
Yeah, but I'm going to go ahead and give it a take a look because at least it looks original.
Yeah, and I think it's Swedish made. I think I saw at the end of the trailer there because it's a different language, obviously.
I thought it was Russian.
Maybe. I saw something about the Swedish Film Institute at the end, but maybe you're right. Maybe it's Russian.
It did have a lot of those award tags on it, so it's possible.
But I think a lot of that had to have been CGI. They have like hundreds of dogs running across the street, and I don't know how it looks really good. So they did that very well.
Yeah.
So either way, it had to be really difficult to film, I would imagine. But
well, yeah, what's the old rule for theater is you'll do fine if you don't include children or dogs, and this has both. So
exactly.
So I'm going to give it take a look. Take a look at the trailer. At least it looks original and looks interesting.
Yeah, and I gave it a drunk watch because I'm like, when I'm drunk, I'd love to watch some dogs running around.
Some dogs taking over the world
exactly.
In organized armies.
And that's something my girlfriend would probably watch drunk too, because she'd enjoy that movie.
True. So there you go. White God. Check it out.
Our trailer reviews for our first show of 2015. Some shitty movies.
Yeah. This is what 2015 has to offer, everybody.
So quick thank you session here on the end of our episode for Facebook. I want to thank some people. Kristen Bazzaio, our wonderful guest from our last episode. She's been active on our Facebook group the past couple of weeks. Someone named Dawn at Dusk. Our old friend Michael McGovern. Chrissy Hensley is a friend of mine. Chris Leonard. In response to me saying, I think the Marvel Cinematic Universe should eventually recast their leads like they do in James Bond. That was an opinion I posted. Ranjan Rajan said, I don't know if you could get away with that with some of the characters that own their roles as much as they do, like Robert Downey Jr. or Tom Hiddleston. But the nice thing about having a universe like theirs is having so many characters to pull from the roster if you can't get one back. And that's true.
Yeah, all they got to do is kill off Iron Man and then we're done.
Yeah, they could just not ever bring back characters and just keep making new ones, which is, I guess that'd be hard to do after a while. You have to keep killing people off and figuring out why they don't come back. But
well, I think the hardest part would be getting audiences to care about these minor characters.
Yeah, exactly.
I think that would really be the trick.
They did with Guardians of the Galaxy, so
they did it, and they're doing it with Ant-Man.
Yeah, there you go.
So they could.
I didn't know anything about him. Tyler McLaughlin, Alan Goodnow, Daniel Hitch, thank you all for your Facebook activity. On Twitter, Mike, or at Jericho, of course, as usual. Our tweets now, someone who favorited us.
Okay, cool.
Hello Stonehenge, and Andy Cowan, who actually I met at the New Year's party I was at. He's actually a host of a podcast called Oh Really Radio with another friend of mine, Michael, and they cover controversial news stories of the week. So they get a little more political and everything on their show. So that's definitely worth a listen. Go check them out at ORLY Radio. That's their podcast, and they might be on the show at some point.
Clever name. And
the YouTube craziness we had over our last couple of weeks is the last thing I was going to mention from our Gamergate discussion, which Gamergate does not exist.
It's not real. It's a made-up thing that everyone says is real.
There are some legitimate concerns about things and in journalism in general, but nothing like what they're describing. They've gone way overboard, and our YouTube channel has become a big discussion soundboard of that last episode.
Yeah, so check out episode 31 on YouTube. We've got people writing us full political essays about Gamergate. It's insane.
The most activity our YouTube channel has ever had, and
the most words that anyone has ever typed to us are right there.
It's pretty weird. But that about does it for this episode.
Thanks again to Ian Cohen for being on and schooling us and making us maybe a little bit more intelligent.
Yeah, we very much needed it, so we appreciate it.
But I know there are two types of telescopes now, so that's the one thing I can take away.
That's It's the only thing you need to take away.
So thanks again, Internet. Join us again next week for what I'm sure is going to be a great episode about what we don't know yet.
We don't know. We'll find out.
We'll see. We'll figure it out.
But have a great new year and stay nerdy, my friends.
Thanks again, Internet.